Ladies and gentlemen, Sputnik presents Ask Dr. Laird your stupid astronomy questions, and here is your MC for the night, Jack Sahora.
Ladies and gentlemen, from New York City, one night only, it is Dr. Laird Whitehill, everyone. Put your hands together. Woo!
Tell me, what do you have for me?
A nebula is a star-forming region.
Yes.
What do you need to be a star-forming region? What's there to make it?
Okay, so what is it? What is a star-forming region? You know, the thing is, star-forming regions are interesting because they are the birthplace of stars, which, of course, you knew that from the first part of the sentence. But the interesting thing is, our star was formed in a star-forming region, a nebula. So what's required in order to form a star, in order to get a star, you need not just one star to be born, but thousands at the same time. So you need a gas cloud that's tens or hundreds of light years across. And that over millions or billions of years, that cloud, dust cloud, condenses until eventually it becomes like a light year in diameter or more, or a couple of light years in diameter, at which point things start to drop out of the gas cloud and become stars. And you get some big stars, you get a lot of little stars, you get medium-sized stars like our own, a dwarf star like our own. But the really interesting thing about that is there's a competition during that time between the big stars and the little stars. And the little stars lose because the big stars essentially blow away all the gases. And then all the stars stop forming. And then, when all the gas is gone, there's no gravity to keep the whole thing together, and the stars go their merry way into the galaxy. So, while we had hundreds, if not thousands, of children that were formed at the same time that our child star was formed, all of the child stars that formed along with us are gone. They're in the galaxy, but we don't know our brothers and sisters. There are thousands of brothers and sisters of our star that we are looking for to this day and have identified none. So does that answer your question somewhat? Okay, and there's much more to say, of course. Say again?
How can you tell if they're brothers and sisters?
How can you tell if they're brothers and sisters? There's an actual easy way to do that, although it's hard. Astrophysicists have a word which only astrophysicists understand. It is the word metallicity. And what metallicity is how many heavy metals can be found in a star. But astrophysicists consider anything heavier than helium a metal. So what you do is you check the metallicity of a star, because the metallicity of a star is what it was given at birth. And that metallicity doesn't change, at least at the surface layers, throughout the entire history, billions of years of the star burning its hydrogen into helium. So you can check to see what the metallicity of our star is, and then you can look to see if other stars have a similar metallicity, and if they do, they would belong to the same group as ourselves. We can't tell if they were near us at any time, because the stars randomly move through the galaxy, so there's no way we can go back in time 4.5 billion years to find the star that was near us at the time. The only check is the metallicity. Thank you for that. Yes? How do you check the metallicity of something far away? Well, that gets into what can you tell? What can you check? There are 400 billion stars in the Milky Way. Basically, we can't see more than 1 billion of them. The other 399 billion we don't see. They're fuzz in the sky, they're light, we see it somewhat, but we can't individually see the stars. So we have a satellite that is designed to see the nearby stars. It's called Gaia. Who in this room is called Gaia? Gaia. And Gaia is a satellite that was launched to look at the nearby stars and tell us as much as they can about those stars. So I'm not sure whether it's checking the metallicity, because metallicity is hard to check. You need a spectroscope. And a spectroscope is something usually built into a telescope, not so much, and you can build it into a satellite, but it's hard to build a good spectroscope inside of a satellite, so you usually have the spectroscopes on the ground. And so ground-based telescopes look at the stars, measure the spectrum, and can tell you the metallicity of every star that they see, but they can't see that many stars in the first place. What was your question?
How do you see the metallicity?
With spectrum. Spectrum. Yeah. Yes.
Dark matter, and how would you measure it?
What is dark matter and how would you measure it?
I also want to know that.
Well, so does everybody else, okay? Nobody knows what dark matter is. It's really interesting. We live in an interesting time. There was a time not too many years ago, maybe a decade or two ago, when we kind of said, we kind of know what the universe is like. But then we missed 95% of the universe when we were thinking we had it all. We are made of matter. Matter is what I'm made of, what you're made of. Dark matter makes up 5 or 6 times more in terms of the percentage of the universe than we do as matter. And there's another 70%, don't figure those numbers out, another 70%, which is dark energy. So all dark energy and dark matter came upon us in the last maybe couple of decades. Dark matter maybe a little bit earlier, dark energy maybe more recently. And we don't know what dark matter is. We don't know if dark matter is anything at all. Dark matter might be, in fact, just a mistake in our equations. There's a thing called MOND, M-O-N-D, modified Newtonian gravitation. I got the abbreviation wrong, but it's MOND, and what it means is maybe Newtonian gravity is maybe a little bit different than it's supposed to be. Maybe Einsteinian gravity is maybe a little bit different. And all we have to do is just tweak the equations a teeny bit, and dark matter disappears. So people are constantly on the search for dark matter. We're looking for it as particles everywhere. We haven't found it. We're looking for it in binary stars. We thought we might have found it. We didn't. In the last year, there has been an announcement that MOND has been found, and another announcement by a competing group of astronomers who said, not so fast. So essentially, not only does nobody know, but the debate is getting really hairy at this point. We don't know. I see there's a hand up, a question, a hand back there.
If the three-body problem is so intractable,
Yeah.
how come that like the solar system doesn't go spinning out everywhere?
Okay, so if the three-body problem is so intractable, how come the solar system doesn't go spinning out everywhere? Is that it?
Yeah, already on
Okay, so the three-body problem is not a problem for scientists. It's a problem for theoreticians who try to describe the motion of three bodies using an analytical equation. For example, a two-body problem can be described by three sets of curves, either parabola, hyperbola, or an ellipse. That describes a two-body problem. You could do that math while you're sleeping. If you add a third body, which also has a mass, there is no known solution analytical solution that you can write down on a piece of paper to the problem. On the other hand, you don't need to. All you have to do is do something that's called iteration. And this is how you iterate. You look at the three bodies and you say, oh, I see three gravitational fields. This one is being pulled by these two. So if this one is being pulled by these two, where will it be next? Oh, it'll be here. Okay? And what about the other two? Oh, well, they'll be there and there. I've just moved each of the three bodies. I've iterated them a teeny bit. I can do it again and again and again. I don't have to solve any problems. All I have to do is put it inside of a computer and iterate. And you can solve for all sorts of bodies. You can do the entire solar system by iteration. You don't have to solve the three-body problem. Does that answer your question? But you can. There are some solutions to a three-body problem if the three bodies are constrained so that one of them doesn't have any mass. Then you can sort of solve that. But the idea of it is a three-body problem is hard to do, so therefore it becomes a meme which everybody understands as being hard. But it's actually not hard for space physicists to figure out where everything goes.
Can you tell us what sort of guy he was?
Can I tell you what sort of guy he is? Yeah, sure. Hi. I'm taking advantage of the fact that I'm old and need to sit. And as long as as long as the camera's on me, I'm good. Okay. Carl Sagan, right. Everything you think about Carl Sagan is true. If he seems too good to be true, it's because he was too good to be true. He was incredible in person when he wasn't trying to be incredible at all. He was, well, so what I experienced was when I used to sit in his office waiting for him to come, I would look at his bookshelf. And his bookshelf was a testament to his curiosity and the things that he understood and knew and was expert or at least well versed in. And those included the classics, biology, chemistry, astrophysics. And I looked at his bookshelf and I said to myself, I wanted to be Carl Sagan. You understand? I really wanted to be him. But when I saw what it took to be him, I realized there was no way that I could ever be like him. What he was inventive. He was, when he spoke, the words that came out of his mouth were new to anyone around him. They were newly invented. His ideas were new. His concepts were new. His way of explaining something was new. It was, and that was just in the privacy of him and me. And in the privacy of a classroom, it was spectacular. He also was, as you may know, extremely kind. So he specialized in taking care of extremely smart, extremely confused people. So, for example, one of the people who used to share an office with me had spent years stoned out on LSD. Carl Sagan took him under his wing, gave him a job, and told him to stick to it. That guy now has a PhD in chemistry. He essentially just raised him up from the dirt. He does that. He was essentially good to all the people around him, kind everywhere he looked, and just as and just as fluent, just as what's the right word I'm looking for? I can't find it anymore because I'm old. Well-spoken, as you have heard him. Yes, it was wonderful to be with him. You're welcome. I realized, and I had never realized this before. You said Jack called me his protege, and I never really accepted the concept of being a protege of Carl Sagan. But Carl Sagan once asked me to substitute for him at a lecture. So the lecture was billed as Carl Sagan, and I was 26 years old, and I substituted for him, and I did great. So actually, I think he knew something more about me then than I knew about myself. Because I've been doing this sort of thing only for the last few years, maybe 10 years. I have been doing this thing, which is called Ask Dr. Laird Your Stupid Astronomy Questions, for about 5 years, since the pandemic. So you're welcome to ask, asinine, stupid, whatever kind of questions you have. Jack, in the back.
I have a question. Could you do me a favor and take one step forward so we can see it? Thank you.
You want me to be well lit?
One more. There we go.
Okay, now I'm so much better lit.
Is it true that all galaxy has a black hole in the middle?
It's true that all galaxies, well, we think all galaxies do, but there could be exceptions. So all is kind of hard. Like if you spill a bunch of thumbtacks on the floor, and then you ask me whether I pick them all up, there's never a right answer to that. There's always a wrong answer. So I can't tell you whether all galaxies have black holes, but to our knowledge, yes, they do. That's great. Yes.
Could you give us your opinion on the Fermi paradox?
Yeah.
Same topic.
So the Fermi paradox is and it's not a paradox per se, but it's a question which has lots of answers. The Fermi, who is the first human being to split the atom, when he was gathered with other nuclear physicists long after the atomic bomb and nuclear and the hydrogen bomb had been invented, he sat around with other nuclear physicists and asked this question: where is everybody? And they all knew what he meant. And he meant, where are the aliens? So, if you look up the Fermi paradox in Wikipedia or elsewhere, you'll find that there are about 100 answers to that question. So you can pick and choose. So what kind of answers would you like? Would you like the most positive ones, or the most negative ones?
Well, I know like the top 5, 7 ones, like the Dark Forest one I think is really cool.
Dark Forest one is good.
But which one speaks to
Well,
you?
the one that speaks to me, the where is everybody? The answer that speaks to me is there's nobody out there. There's nobody out there at all. Now this is how you can prove it to yourself, okay? There's a thing called the Drake equation. Have you ever heard of that? Okay. Frank Drake was an astronomer who also lived on the same floor as Carl Sagan and myself at Cornell. And he became famous for coming up with an incredibly silly but incredibly important equation. He said, I can tell you how many alien life forms there are out there right now through this very, very simple equation. And it's a combination of probabilities that are multiplied by one another. For example, first one, what's the probability that a star has a planet? When he wrote that equation down, nobody knew, because nobody had ever seen planets around other stars. But at the time he said that, we came up with a number, and we came up with a number that was 50%, which turns out to be around the right number. What's the probability of a star having a planet, a rocky planet, you can assign a number to that, okay? What's the probability that rocky planet is in a habitable zone? You can assign a probability to that. Now you're assigning probabilities. These numbers we know now. We didn't then, but we assign good numbers to them, like 50%, 25%. We assign good numbers, and you're going to multiply that by the number of stars in the galaxy, right? So far we're good, but then you start to get into things that we really don't know. For example, do we need, and by the way, the question is not, is there alien life? That question, in my opinion, is yeah, sure, absolutely. The question is there alien life capable of communicating with radio? That is the question. And the answer to that depends upon a lot of other factors that we don't know how important they are. For example, is the Earth's moon important for there to be life, intelligent life on this planet? For example, if you take away the moon, you get Mars. Mars is tilted like this. The Earth is tilted like this. The difference between the Earth and Mars is Mars does this every few million years or so, and the Earth does this. So if you want something to evolve dealing with winter and summer, you better keep winter and summer the same over evolutionary time. So if we had to evolve where we had to suffer for a 6-month winter, we might not have evolved to be the people that we are today. So a moon, then you go into the biology. And if you know anything about biology, and I know virtually nothing, I know enough to know that it's a lot more complicated than astronomy. If you look at what had to happen in order to get us, it's totally improbable. Every step of the way. And if you want, at this point, if you really, now you could say, well, evolution did this. Of course it did. But how did it know to do this? Okay, it could have gone any other way. And by the way, if you think intelligence is selected for, have you noticed that we have nuclear weapons? So that's not so intelligent. So we might be a blip in time. And so if intelligence is selected for, it might not last very long. So the very last number in the equation is a big L. All the other ones are small f's. Fraction of this, fraction of that, and then there's one big L at the end. And that big L is longevity. And longevity says, how long does that civilization live before it kills itself? And the thing is, we only have one example, and it's not very good because it doesn't look like we're going to make it. I think you'd all agree. So if there's any, and if our number is not thousands. Our number is since we invented radio. So how long is that going to be? Maybe 150 years. Our L, if we all disappear around the middle of the century, our L is 150, which means if it's 150, there's nothing out there, nothing. On the other hand, if the L is millions, then there are plenty of them out there. So we really don't know. So when I say 0, I'm thinking that we are the norm and that anybody who figures out atomic energy will ultimately destroy themselves. And so that's my pessimistic point of view. It has nothing to do with biology. It has all to do with that L. I still need your questions. I think you got the idea so far. As you've noticed, I have answers to questions. You need to provide the questions. Yes?
Who is the most controversial astrophysicist and why?
Who is the most controversial astrophysicist and why? Well, I would say Michel Macau, I can't say his name very well. He's not really controversial so much as he amps it up. So So I really, and I don't pay attention to him, so it's not fair. I think the most controversial astrophysicist is this guy Avi Loeb, who is this tenured professor at Harvard, who has gone on record. Has gone on record as saying that probe was an alien probe, and he has gone further and said that he's recovered pieces of an alien spaceship in the ocean. He's gone dredging for the things, pulled up little spherical modules, and says these are alien technology. So that's pretty outrageous, and he doesn't go very far in my book, but he's using the money well, so that's good. Yeah. Yes. Yes.
That Kamehameha has neither a parable, a hyperbole, or an ellipse?
Say that again, please.
Do you agree with his assertion that Kamehameha has neither a hyperbole, parable, or elliptical pattern?
Yeah. Do I agree with his assertion that the orbit of Oumuamua is not a conic section, which is what all those three are together: hyperbola, parabola, and ellipse. And I don't. It's not his assertion. It's a measurement. So he didn't assert that it's not. It is truly not one of those three. So the only question is, how did it accelerate without rocket engines? And the answer is a little hard to answer, because if it is a comet, you would see the cometary debris, the cometary tail. You would see it. We don't see that. So the question is, what is propelling that object if it's not an alien spaceship? And the answer tends to be something like, well, it could be frozen hydrogen, which would not leave a trail. It could be frozen nitrogen, which would not leave a trail. So there are answers to his statement that you can't do it without rocket engines. It also could be a sail, a solar sail. Yes.
There is this project which is called Breakthrough Starshot, for sending microscopic.
Yes.
What do you think about it from professional perspective?
Yeah. Okay, Breakthrough Starshot. Breakthrough Starshot is a concept put forth by a group of people that are trying to figure out a way to get to the nearest star sort of sometime in the near future rather than the far, far, far future. So, in order to do that, they propose that they create thousands of solar sails, and that those solar sails be propelled by lasers towards Alpha Centauri. And the problem with that is there's no known way to do that yet. For example, if you're going to propel a solar sail, which may be this big, 4 light years, and you're going to accelerate it with lasers, the chances are that you're going to burn it up before you begin, because there's no known substance that can take that amount of heat. The other thing is you have to be able to create a radio transmitter that's going to transmit back from 4 light years. That's a difficult thing. You're going to have to use all of those starships, all of those things as an array to send it back. So there's a lot of technology that is yet to be worked out. And I am a professional pessimist. So I can tell you that's not ever going to happen. But that's not their point of view. They think it's continuously worth a star shot. Yeah. Yes. Here.
Do you think it's a good idea to go to Mars?
Do I think it's a good idea to go to Mars? Do I think it's a good idea to go to Mars? No. I think it's a great idea, just like it wasn't a good idea to go to the moon. Okay. why did we go to the moon? We went to the moon to beat the Russians. And incidentally, we learned about the moon, and we learned about the origin of the solar system. That was a byproduct. Going to Mars, the byproduct would be we find out if there's life there. But the product is that we impress everybody, and it's all about economics, it's all about politics. But from Elon Musk's point of view, it's about making a second home for humanity. And I would point out, just between us, that I don't think we would survive very long without a tree. I think if we can't plant trees there, and we won't be able to plant trees there unless they're underground, then what's the point? If we're going to try to plant trees above ground where the sun doth shine, that ain't going to happen. So I don't think it's a place that humans can spend any time. We can go there, we can build some sort of colony, but the question is whether we can move a portion of humanity there in such a way that they become self-sufficient and never have to come back to Earth for supplies. I find that to be not likely. Do you have a question? Speak up. How are stars made of? What are they made of? Okay. Stars are made of hydrogen. Now, hydrogen is something that you don't see every day, but you do see it when you drink water, because water is 2 parts hydrogen and 1 part oxygen. So hydrogen is in the water you drink, but in the sun, it's just hydrogen, no oxygen, just the hydrogen. And the hydrogen is there, and that's what the star uses to make light. It takes the hydrogen and it bangs it together, and in the banging together, the 2 hydrogens form a helium, which is different, and the helium makes something very hot, and it makes the sun very hot, and the sun then keeps us warm as well. So the sun is made of hydrogen, mostly. Little helium, very little else.
Diogo has a question.
Did I answer your question? Did I answer your question?
No.
Yes.
Thank you. Okay, next. Yes.
Is the nuclear fusion project realistic? I mean, getting energy from the same reaction.
Do I think that nuclear fusion is reasonably realistic? Is that the question?
Yeah.
Well,
I mean, is it possible to?
the joke is it's always possible 30 years from now. Okay, and that's been true my entire lifetime. But nevertheless, I see lots of nuclear fusion projects being activated and proposed and executed. So I am hopeful that within 10 years, not 30, one particular project that I'm interested in particular might come to fruition. The problem with nuclear fusion is that every story you've been told is a lie. And the lie goes like this. We just produced more energy than we put in. We've just gotten more energy out than we put in. We've achieved it. We've achieved ignition. But that's the lie. What they did is during the split second that nuclear fusion occurred, that was true. It just took a couple of days and 100 times more energy to charge the capacitors, so the actual amount of energy that was required was 100 times more. So they're 100 times. So the lie is about 100 times worse.
Rebecca has one more question.
Yes. I'm coming to you. What? Does Jupiter have a ring? She asks, and the answer is yes. The Jupiter has a ring. Saturn has a ring. Uranus has a ring, Neptune has a ring, and there's even some small planets. I'm not forget the name of it. Another small planet, one other planet has a ring. So planets have rings all the time. Our planet doesn't have a ring. Mercury doesn't, Venus doesn't, Mars doesn't, but the rest of them do. Okay. Pluto does not have a ring. Yes? What is what? What is a wormhole? A wormhole is a theoretical construct consistent with general relativity, which isn't real, in the sense that you can't make one. But that doesn't mean that you can't imagine them. In order to make a wormhole, you need negative energy. There's no such thing as negative energy, but it's theoretically possible given the equations. So something goes in, it comes out the other end, and it's someplace else in the universe. But you can't do that.
In terms of the multiverse,
The multiverse?
do you think that's something that people make up just to sound more interesting? Is there any real theoretical evidence?
Oh, no, there's no theoretical evidence for multiverse. On the other hand, there's no way to prove or disprove it, which means it's sort of outside the realm of science. On the other hand, it's consistent with theories that have been put out. For example, the universe began as a Big Bang, right? So, okay, but the Big Bang doesn't work unless you add something to it as part of the stew, and that's something called inflation. And inflation is required in order for the Big Bang to ever happen in the first place. Because what you need is, you need space to expand so much more than you could possibly imagine in our little brains. The only way you can imagine this is if I gave you some numbers, 10 to the minus something and 10 to the plus something else. And if I told you those numbers, which are very, very outrageously large, like numbers like 10 to the 26 is a number that comes into this, which is a ridiculously large number, which is the amount that space expanded in a ridiculously small amount of time. That's inflation. Well, inflation, if you imagine, okay, how did inflation begin? And so what you say is, well, it didn't begin. It's always going on. Because you don't answer the question, how did it begin? So you say, well, inflation is out there. As soon as you say it's out there, you got multiverses. In other words, here's a universe, there's a universe, everywhere a universe. And then there's one other argument which I personally like, which is we are too specialized as in terms of the physics that make us work for that to be a coincidence. So if in fact the fact that we exist is not a coincidence but just as random phenomenon, there must be other universes in which other things work differently.
So, following on, initially you said there was only one human race.
One race.
I'm just curious, if you think there is a possibility of a multiverse.
Yes, possibility of multiverse.
Yes, there are other species, other aliens, so to speak, because hardly everything can happen.
Well, if you want to go down the apparently everything can happen rabbit hole, let's go there. Is space infinite or not? I'm asking you because we don't know, so I'm asking you. Yes. Now that's a good answer. It's my favorite answer. Okay. And by the way, if you really want to find a way to go to sleep at night, trying to think about infinity will do it much better than sheep. Okay, because it's a lot harder to get your head around that one. So if the universe is infinite, then and if there's an infinite number of multiverses, which by the way doesn't make that much sense to me. It's either infinite and there's one, Or how do you get an infinite number of infinite universes, which is not outside the realm of what people say. An infinite number of infinite universes. Because in mathematics, it is well known that you can have an infinite number, you can have many infinities. For example, the number of integers is one infinity. The number of points on the line is another infinity, which is greater than the number of integers on the number system. So there's two kinds of infinities, and they can fall within one another. Yes. Are there what? She asks, on other planets, are there living things? And we don't know. And we don't know if there are living things on other planets. And so we are going to Mars to find out, and we're going to Europa to find out, but it will take a long, long time. It may take many tens, hundreds of years to find out. We don't know the answer. And we may never know the answer. And we may find out. We never will know until we find out. So I can't answer your question. When you grow up, you can ask the same question, and maybe you can be involved in answering that question. It's a very difficult question and very worthwhile. Go for it. Okay. All the way in the back.
Philosophical topics. What's your take on free will?
What's my take on what?
Free will.
Free will?
Yeah.
What's my take on? I'm not good on that. I'm absolutely sure that I have free will, except when I start repeating myself, and then I'm not so sure. Otherwise, I'm a test case, so I have no opinion, really, and I don't know that, and I do not know whether there is any opinion out there worth believing. There's all sorts of conversation, but I don't think there's any resolution to the question. You can ask the question, well, doesn't quantum mechanics give us free will? That is not answered per se. So I don't even know that whether quantum mechanics gives us free will. Okay. Yes.
Perhaps this is more physics, but we might not be able to prove, for example, simulation theory, but are there any observations that you've seen that might give us the intuition that simulation theory might be true?
Are you saying do we live inside of a computer?
For example, yes.
Okay.
What observations might lead us
No. Here's an observation we can use to see if we live inside of a computer. Welcome to the Starship Enterprise. Here is the transporter room. Okay? This is the place where you stand to be transported. Let me tell you how it works. Every molecule in your body is disassembled. There's another word for that. You are killed, okay? And then you are reassembled someplace else, okay? So, the question is, are you okay with that? No. And why aren't you okay with it? Because you and I, although I'm an atheist, maybe you're an atheist, at the same time, I don't know about that, but I kind of think I've got a soul. I don't think that not a soul that's worth preserving, in heaven, but whatever it is, it's not defined. Humanity has not yet, and I conjecture, never will define consciousness in a way that could say, and we can transfer it to a computer. I don't think anybody will ever really be convinced that my consciousness can be conveyed to a computer. And I don't think you would either, given what the experiment I just put you through. Right? Okay. Yes.
Carl Sagan mean when he said that we were made of star stuff?
What did Carl Sagan mean when he said we're made of star stuff? But that is a simple question. Are you looking for a simple answer, Or are you looking for a more complicated one? What do you think he meant? And I'll take it from there.
I kind of assumed that he meant that matter on Earth is the result of like an exploded nebula or an exploded supernova.
Yes, matter on Earth is the result of an exploded supernova. So, don't you like that? Isn't that a good enough answer for you?
Could you sort of explain how that works?
In other words, you want to know how not so much. So you buy totally into the idea that we all existed at some point within a star, and we're all blown out of that star as a result of a supernova, and the elements that comprise our body once existed inside another star. You buy into that, right?
I've never seen it happen.
And you never will. You have this. Your lifespan is 100 years. If you want to see that happen, you have to wait millions of years. The average number of supernovas that occur in the Milky Way in a given year is none. The average number that occur in our Milky Way in 100 years is 1. So you won't see one in your lifetime, more or less. And the chance of it being anywhere near is pretty much close to 0. But on the other hand, there is a nova that's going to occur any minute now. And that nova is in this, you'll be able to see it in the sky. That nova is in a constellation, Corona Borealis, and it's not a supernova, and it's not going to light up the sky in any kind of spectacular way. But when it goes off, you'll be sure to see it in the newspapers, and it will be giant clickbait, because you won't be able to see it in the sky unless you happen to be a shepherd who knows the sky already and can see, oh, that star, it's brighter than it used to be. Oh, so that's a nova. That's not a supernova. But it's due to happen any day. So that's why I mentioned it. Really. In fact, it's overdue. Yes. Further part of the question.
So we know like how old the universe is.
We know how old the universe is, yes.
We know how old our own star is.
We know how old our star is.
And we know how old the Earth is.
And we know how old the Earth and the star are about the same age.
So, by Carl Sagan's work, we come from a supernova.
We come from a supernova.
That means that a star was born, grew, died, exploded, and then our own star and our own planet started.
Yes, right.
How many times has that happened?
Well, we're not the result of one supernova. We're the result of many. It is not thought that our Earth was created by a single supernova, but a series of supernovas over time. And in fact, it is thought that not only that, but there's something called a kilonova, which is new in the last 5 years or so. And kilonova is when two neutron stars smash into one another. And it's thought that most of the gold and heavy metals like that on this planet didn't come from a supernova, but came from a kilonova. So basically, a lot of stuff went on before the Earth got made, not just one. And then supernovas come in various sizes. But I want to answer Orion here. He's had his hand up. I'll come back to you, okay? Orion. Oh, not Orion. I'm sorry. What's your name? Rebecca. That's Rebecca. Say again.
That was part of the show. Cost us a fortune.
That was a supernova.
That was a supernova. That was the Big Bang, actually. I think that's what they meant to.
It's probably okay, you guys.
What was your question?
Still works.
How many drinks have you had?
Have shooting stars ever touched on Earth?
Have shooting stars ever touched the Earth? And the answer to that question is, first of all, there's some beer on the floor here now. Okay, this one right now. Beer on the floor. Have shooting stars ever come to Earth? And shooting stars come to Earth all the time. All the time. There are little shooting stars, bigger ones, bigger ones, bigger ones, bigger ones, bigger ones, bigger ones. The little ones come to Earth like dust. See the dust on the ground here? Some of the dust on the ground is shooting stars. Some of the dust on the ground is shooting stars. Shooting stars lay on the ground everywhere, but you don't see them because they come down like dust from the sky. Shooting stars that come down as rocks do come down, but only every now and then. Maybe every other day, there's a rock that comes all the way down and lands on the Earth, and we call that a meteoroid. Meteorite. We call that a meteorite. When it's up in the sky, it's a meteoroid. When it comes down, it's a meteorite. When it's going through the sky, it's a meteor. And it comes down, sometimes it's little pebbles, sometimes it's bigger, sometimes it's bigger, sometimes it's bigger, sometimes it's much, much bigger. In fact, it can be any size at all. So they do come.
Could the Earth ever separate with a shooting star?
Could the Earth ever separate from a shooting star? No, I'll tell you. Along the shooting stars right now are really, they're not very strong. So in long ago, before there were dinosaurs, before there were fish, before anything was on this planet, there were things that came down from the sky that were so terrifying that it could split the Earth in half. And in fact, there was one, and it hit the Earth so hard that it broke the Earth into two pieces. And the two pieces one of them we call the Earth. The other piece we call the Moon. The Moon was once part of the Earth, but a big asteroid, in fact it was a planet, came by and it hit the Earth and it broke the Earth and it threw the Moon into orbit around the Earth, and that's how we got the Moon, which, by the way, means that the Moon is very rare. It's not the normal sort of thing. It has happened maybe once, maybe twice in the solar system, and it would have to happen on another planet for intelligent life perhaps to exist. How much damage would it make? It would be horrible. But it only happened a long time ago. Oh, it would kill everything. Everything. The planet is gone. It starts with a new planet. The whole planet turns into a giant volcano. And then the whole planet gets hot, and the whole planet turns into molten rock, and then the whole planet takes millions of years to cool down again. It only happened once. And that was at the very, very beginning of the solar system when the sun was still just a little child. It happened so long ago, it's never going to happen again. You don't have to worry about it. Never going to happen again. Yes?
What are the most interesting projects in astrophysics that I need to follow?
What is the most interesting projects in astrophysics?
That you follow, that you're interested in?
That I follow, yeah, of course. I guess from my point of view, the thing that I want to know most is whether there's life out there in the universe. And we're not doing very much about that. So there's no project at this point that has been planned or even proposed that would answer that question. So the only way that you can find that out is if you go to Mars with a shovel, take a scoop of sand, bring it back, or analyze it there, even then and there. But that would be Elon Musk, right? But that's not so much science as it is politics. So, but in terms of what else, I'll think about it. It's a good question. Yes.
What about Voyager?
What about what?
Voyager.
Voyager. What about Voyager?
Well, it's going out there. It's the furthest.
Voyager is going out there. It's the furthest. But aside from that, and that it sets a new record every day.
Wasn't the concept Sagan's voice and
Yeah.
various contributions from many countries. Wasn't it the idea that Voyager would sally forth and see what intelligent life is?
Oh, no. Voyager is a project, a scientific project that has nothing whatsoever at all to do with Carl Sagan. What he did is he put a plaque. He did two things. I mean, certainly he had some input into the project, of course, because he was that kind of person. But in terms of what Voyager was intended to do, it had nothing to do with alien life. It had everything to do with exploring the solar system, which it did very well. And then as its supplementary job, its job was to explore interstellar space, which it has been doing. And it has one more purpose, which is to impress you with the fact that aliens at some point in the future might come upon it and discover it and say, aha, there used to be life on planet Earth. But that's just a story. It's not, it was never intended to be a reason. But it made a good publicity, and Carl Sagan created, and Frank Drake created a very great story, the Pioneer spacecraft and the Voyager spacecraft. It's great stuff.
Well, it was very inspirational to me when I was young. I believe that.
No. If you want to tell a good story, what you tell people is that this is the relic of mankind that will survive long after we're gone, and somebody in the far distant future could come upon it. But then because you're an adult, you can ask one further question: what's the probability that an alien life form could find it? And you can and so here's one fact: it's going to come nowhere near any star in the foreseeable future. And we're talking light years. So light years away from any possible star in the foreseeable future. And then, of course, you have to come past the star that is harboring, communicating, star-faring life forms. So it would have to survive for billions of years for the probability to be enhanced to the possibility that it might be conceivable that something might find it. So if you add an infinite number of years, you can outweigh the probability of it never happening. Otherwise, there's no chance. Believing. What did Carl say? Unlikely. Yes. Because Carl Sagan says unlikely. He was the world's first astrobiologist, right? And maybe we don't know that field exists at all. So what you can do is you can multiply. Let's say the probability of there being intelligent life in our galaxy is 1 trillion to 1. Okay? That's pretty low, right? But there are 2 trillion galaxies that we can see. So the odds are, so for every trillion galaxies, there's an intelligent life form. So all you have to do is multiply by a large enough number to get a non-vanishing number that's true. And if you go with infinity, then there's no reason to suspect that the answer isn't. Of course there is. And I believe of course there is. The only question is, how probable is it? Ken?
It's very improbable that I'm going to win the lottery, but someone will.
Yes, someone will. I have a lottery ticket in my pocket. Oh, I do. But I always buy 2 lottery tickets, okay? Yeah, because see, the chances of winning is 1,000,000 to 1. But if I buy 2, I've already cut out half the people. I figured that's a bargain. Right? Okay. I think, yes.
Do you think the universe is cyclical?
Do I think the universe is cyclical? Is the universe cyclical? It's possible, but unlikely. I don't think it is. I think we've got one universe, we have to treat it kindly. But the fact is, dark energy is an unknown. We don't know what it is, we don't know what it's doing. And if dark energy decides to change its mind and become more negative instead of more positive, then the universe could be cyclical. So cyclical is not ruled out. It's just not a very popular thing at all. This microphone seems to have gotten stronger. It's louder now, and I'm holding it further from my face. Okay. Do we have more? Okay. You.
I have a question about gravity.
Gravity.
How does mass distort and bend space-time?
How does mass distort space-time? I mean, it's a hard question because Einstein answered that, and I'm no Einstein. There's a phrase. Mass tells space-time how to curve. No, let me work on it. How does mass curve space-time? Well, gravity is in its Einstein's theory of general relativity. You don't hear the word gravity in there. In that, so gravity is thought to be a force, but gravity is not a force. It's a bending of space-time. So for example, let me demonstrate. This is a wet, damp rag. Okay, it fell, right? You would say it fell because of gravity. I would say, well, I wouldn't really say because it's hard to say, but I would say that it followed the path of curved space-time. I threw it in a particular way. It followed the path of curved space-time to go where it ended up. So when you throw a satellite into Earth orbit, it's accelerating around the Earth, just like this accelerated. The satellite accelerates, but it doesn't change its speed. Now, if you're like everybody else, what I just said makes no sense. It said it accelerates, but it doesn't change its speed. Does that make sense to you? Clearly not. Okay? So, how does something accelerate without changing its speed? Well, I'll give you an example. You're in a car at a constant speed, and you're going around a curve, and you're being pushed against the side of the car, like as if you're accelerating. That's because you are accelerating, not as if. Acceleration is defined, and you have to go to freshman physics to know this. Okay? Jack, the microphone has been turned up louder, and so we're getting feedback.
Can you take 2 steps back?
Okay.
You have to stand behind the speaker.
Oh, I see.
Because nobody could hear you in the back.
Okay, I see. Thank you. You turned off the microphone. Okay. So when something is changing its speed, that's acceleration. But when it's changing its direction, that's also acceleration. Acceleration is defined as the change in velocity. And velocity is not what you think it is. Velocity is speed and direction, both. So you can change either your speed or your direction. As it turns out, Earth satellites are not changing their speed, but they're changing their direction. So they are accelerating around the Earth. And guess which direction they're accelerating in? Down. They're always accelerating down. They're never accelerating in the direction they're moving. They're accelerating down because they're being pulled down by this thing you call gravity. But no, it's following the curvature of space-time. There's no gravity. It's just curved space-time. I don't know, that didn't answer your question at all, but it's at least a try. Right? Right. My hand is weird. More questions? Yikes. Yes?
During inflation,
the
space-time or space accelerate or
space expanded.
Faster than the speed of light.
Space expanded faster than the speed of light, and this is a crazy thing, of course, but the speed of light prevents things from going any faster than it. But that doesn't mean that space can't expand faster. So here's a really crazy thing. The age of the universe is 13.8 billion years. 13.8 billion years. So if you think about that, nothing could be further away from us than 13.8 light years. Nothing could be, if you think that way. But you're thinking wrong, because space can take things with it and expand things so that things are further away from us than 13.8 billion light years. In fact, the edge of the observable universe is 46 billion light years. We can't see quite that far, but so we know that there's stuff out there at 46 billion light years that has moved faster than the speed of light. But it's hard to explain how something can go faster than the speed of light, and yet you can't go faster than the speed of light. Both true. Yes?
Do you think the universe will end, and how do you think
Do I think what?
the universe will die?
Do I think the universe will die?
And how will it die if you do?
There's a book that describes 6 or 7 ways the universe could die. My favorite way is the idea that there is what's called a position of stable equilibrium. We live in a world which seems to be stable in the sense that it doesn't get any hotter, it doesn't get any colder, more or less any time. But things could cool off. The universe is actually known to be, or thought to be, sitting in a puddle. And we're down here. And there's a peak we can't climb. But on the other side of the peak, there's a deep valley all the way down here. We're here, and we're never going to go here unless we tunnel through the hill. The probability of tunneling through the hill is non-zero. We could end up on the other side of the hill, and if we did, the universe would disappear. But it wouldn't disappear suddenly. It would disappear in one spot, and then it would propagate outwards at the speed of light. And when it got to your toes would disappear. And you wouldn't notice it because, the nerves in your body don't transmit information that quickly. So you wouldn't notice that your toes had disappeared before your head disappeared. But that is one way the universe could disappear. Right. Jack, the MC, has suggested that perhaps the appropriate thing for me to do is to take one more question, and then you should all go to the bar and get drunk and have some drinks with me, and I'll continue to answer your questions, but on a one-to-one basis. Jack?
I have one question that nobody would know to ask. We've talked a lot about science and astrophysics and the importance of Carl Sagan, right?
All that.
What is Carl Sagan's importance to you when it comes to your love life?
Oh. What is Carl Sagan's importance to me when it comes to my love life?
Yeah.
There's multiple answers to that question. Which one are you fishing to?
The best one.
No. I mean, really.
About your girlfriend.
My girlfriend.
Your heart was broken, and you went to Carl.
Oh, okay. All right, so that. So Carl Sagan was my advisor. What he talked to me about was not my thesis. It was my girlfriend. I talked to Carl Sagan for 2 years about my girlfriend. He was my therapist. During the last 2 years that I was doing my thesis, I really was doing a terrible job, and Carl Sagan was counseling me. So that's the answer you were fishing for? Okay.
Ladies and gentlemen, Dr. Laird Whitehill!